Let's compute the following 6 quantities, and we'll try to do this without using a calculator. First off, e to the I pi over 3. By definition, that is equal to cosine of pi over 3 plus I sine pi over 3, which is the square root of 3 over 2, or sorry, cosine of pi over 3 is a half, so 1/2 plus I square root of 3 over 2. And so that is the first one um, in red. Next, let's do the one in green down here, e to the 2 plus 5i. So same idea, e to a complex number. By definition, this is equal to e squared times cosine of 5 plus I sine 5. And the 5 here means 5 radians, not 5 degrees. So we have e squared times the cosine of 5 radians plus e squared times the sine of 5 radians, and that times I. So that is the answer. There's no particular shortcut to doing this without a calculator, so let's go ahead and do that. So to do this by calculator, we want everything in radians, so let's confirm that. So here the mode of the calculator is in radians, so that's good. And so the real part would be e squared times the cosine of 5 radians, which works out to be about 2.096. So approximately 2.096. The imaginary part will be e squared times the sine of 5 radians. Now this might look funny because there's no pi inside of the sine function, but just 5 radians, whatever that works out to be. And that works out to be about negative 7.086. So negative 7.086 times I. Now let's check to see if that actually works out. So let's do that in the calculator. If I take e to the 2 plus 5i, we get 2.095, that's the first part, minus 7.0, and you'll imagine 855, and that'll be the second part. So that is all this to say that the answer in the calculator confirms what we just did. Okay, now let's do the logarithms. So first off, in blue, let's get the logarithm of 4 minus 4i. To do this, I first have to convert 4 minus 4i into trigonometric form. So 4 minus 4i is down here in the fourth quadrant. The distance from the origin is 4 square root of 2, and the angle from the positive real axis is negative pi over 4. And that's important because we need to have an angle that's between negative pi and plus pi. So 4 minus I can be written as 4 square root of 2 times e to the negative I pi over 4. And so by definition, that's equal to the natural log of 4 square root of 2, whatever that works out to be, minus I times pi over 4. And so that is the logarithm of 4 minus 4i. Now let's check to see if this actually works. The natural log, whoops, wrong button. The natural log of 4 times the square root of 2 is equal to about 1.7328. If I take the logarithm, sorry, it should be natural log of 4 minus 4i, I get 1.7328, the same part we have here, minus this other thing, and the other thing starts off as pi over 4. So if I compute pi divided by 4, it starts off as 0.78. You see those are the digits we have here, and we have a negative, so negative I times pi over 4. So that confirms what we get in the calculator. Next, in Brown, let's do the next one, the logarithm of negative 5 plus 12i. So we do this one over here. Negative 5 plus 12i is going to be up here in the complex plane. So negative 5 on this side and 12 on this side. So the distance from the origin is 13. And now I need to figure out this angle over here. To figure that angle, so I need the angle. Let's first figure out, remember from pre-calculus that the tangent of the angle theta is equal to the b over a, so negative 12 over 5. And so therefore, theta, the mistake would be to simply say that this is equal to the arctangent of negative 12 over 5. Now that's incorrect because arctangent always returns values between negative pi over 2 and plus pi over 2 down here. So the arctangent has to be in the first or fourth quadrant. So arctangent of negative 12/5 turns out to be this angle here. That the angle that I'm drawing here is the arctangent of negative 12/5. Then I need to take this and add pi to get the angle here that I'm drawing in bold brown. So theta is equal to the arctangent of negative 12/5, but I have to add pi to make sure that I'm pointing in the right direction in the second quadrant and not in the fourth quadrant. So using the work that we have here, the distance from the origin is 13, so I have the logarithm of 13 times e to the I times arctangent of negative 12/5 plus pi. And so by definition of the log function for complex numbers, this will be the natural log of 13 plus I times the arctangent of negative 12/5 plus pi. Okay, so let's see if that works out in the calculator. So natural log of 13 is 2.565, and the arctangent of negative 12/5 plus pi is about 1.96558. So let's see if this works out. So let's take the natural log of negative 5 plus 12i, and we get 2.5649, the first part, plus the second part, 1.96558i. And so the answer matches what we got in Brown. Okay, finally, let's do the last two exponential problems, where I have a base other than e. Let's now tackle the next problem. We'll do this one in blue. Actually, let's do this one in orange. E minus 3 minus 3i squared root of 3 raised to 2i. by definition, this is equal to e to the 2i times the logarithm of 3i minus, 3 minus 3i square root of 3. And we compute the logarithm in much the same way that we just did the last two problems. So let me do that at the bottom of the screen. 3i, or 3 minus 3i square root of 3. If I plot that in the complex plane, is going to be down here. This length is 3, this length is negative 3 square root of 3. So the distance from the origin is 6, and the angle here is going to be negative pi over 3. So this is equal to 6 e to the negative I pi over 3. So we have that this is equal to e to the 2i times natural log 6 minus I pi over 3. Okay, let's multiply out the complex number on top. First, 2i times negative I pi over 3 is going to be plus 2 pi over 3. And the imaginary part will be plus 2i times natural log 6. And so this will be equal to, by definition, e to the 2 pi over 3 times the cosine of 2 natural log 6 plus I sine times 2 natural log 6. And if we break this up into pieces, this would be e to the 2 pi over 3 cosine times of 2 natural log 6 plus I times e to the 2 pi over 3 times the sine of 2 natural log 6. And so that's the answer. Let's plug this into a calculator. So we hit clear here, and let's see. So the real part would be e to the 2, oops, wrong button, e to the 2 pi over 3 times the cosine of 2 times the natural log of 6. So it's a very unusual expression where logarithmic expression is the angle, and we get negative 7.34. The other one will be e to the 2 pi over 3 times the sine of 2 times the natural log of 6. And that works out to be negative 3.473 approximately. Okay, now let's see if this actually works out. So plugging in, we get 3 minus 3i times the square root of 3 raised to the 2i. And this works out to be exactly what we expected. Negative 7.34038 is the real part, and negative 3.4273 is in the imaginary part. So that works out as expected. Finally, let's tackle this last one, 3 minus 4i to the 2 plus I. I'll say right at the start that this one's going to be a mess. This one's equal to 2 plus I times the logarithm of 3 minus 4I. Now the logarithm of 3 minus 4I, let's draw that in the complex plane. That's down here in the fourth quadrant. So this is 3 and negative 4. The distance from the origin is 5, and the angle theta is going to be equal to the arctangent of negative 4/3. The reason is because we always know that the tangent of theta is equal to y over x, which in this case is negative 4/3. And if I take the arctangent of both sides, I get that theta is equal to arctangent negative 4/3. The angle is in the fourth quadrant, which is perfectly fine, between negative pi over 2 and plus pi over 2, which is exactly where I want it. In a previous example, I believe we had an angle which was not in the first quadrant or fourth quadrant, so we had to make an adjustment to make it fit in the right quadrant. Okay, so we have that this is equal to E times 2, well, so we have that 3 plus 4I, getting ahead of myself, 3 plus 4I is equal to 5 times e to the I, and the angle is the arctangent of negative 4/3. And so we have 2 plus I, and then taking the logarithm, we have natural log 5 plus I times the arctangent of 4/3. Okay, so let's multiply this out. The real part is going to be 2 times the natural log of 5. And then the last terms, I times I gives minus arctangent of 4/3. The complex part will be I times, the inner part will be natural log of 5, and the outer part will be plus 2 times the arctangent of 4/3. And so this will be equal to E times 2 natural log 5 minus the arctangent of 4/3 times the cosine of natural log 5 plus 2 times the arctangent of negative 4/3. And I realize that I have not been writing minus 4/3, so let me fix that. This is minus 4/3, which becomes minus 4/3 here, which becomes minus 4/3 there and there, which becomes minus 4/3 here. So I apologize for that. And then plus I times pretty much the exact same thing. So I'll just copy it. Except that instead of cosine, I have sine. And so this very complicated expression would be 3 minus 4I raised to the 2 plus I. Okay, now let's plug into a calculator and see if this actually worked, and let's hope it did. So first off, we have e to the 2 times the natural log of 5 minus the arctangent of negative 4/3. So So let's see. So the next parenthesis completes the exponential term times the cosine of natural log 5 plus 2 times the arctangent of -4/3. And so this will be the real part, 61.302. Okay, so let's plug in the calculator and see if this is what comes out. So 3 minus 4i raised to the 2 plus I power. And we get 61.302 as expected. And the imaginary part will be exactly this term that's left, minus 15 point something. And you can plug that in the calculator and confirm that that works out. So that's the computation of these expressions. And the last two expressions, well, we had to use the techniques developed in the first four.